Right, good morning everyone, and let's start the physics lesson. We will go through the material here in terms of questions and answers in a problem-solving context, and if there are various theory things that you want further explanation with, please ask me at any time, and then I can expand to as much detail as is necessary to clarify any such point. Begin by looking at question number 1 here, and at any point if you have a question, please ask me. A ball on the end of a cord of length 1.20 meters is swung in a vertical circle. So it is important to pay attention to. The circle here is in the vertical plane. And the mass of the ball is 0.250 kilograms. 0.250 kilograms. And when the ball is in the position shown, which is somewhere here, its speed is 4 meters per second, which is what they have indicated in the diagram. Acceleration due to gravity on Earth, we are supposed to take it as 9.81 for this question. Calculate the size of the centripetal force acting on the ball at the instant shown in the diagram. Now, that is simply looking at even your resource sheet, but you didn't have to look at it because it is such an important equation. It's simply applying the equation that centripetal force is equal to m, the mass, times v squared, that's the speed squared, divided by the radius of that circular path in meters, and you put all quantities in there, in that equation, in their SI unit. Now, substituting the numbers into this equation then, to get the centripetal force, the mass, we were told, is 0.250 kilograms, and of course that's in its SI unit. So it's 0.250 times v squared divided by the radius of the circular path. Now the v squared here will be 4.00 squared divided by the radius, which is 1.20 meters. And if you do that calculation, that's 4 divided by 1.20, 4 divided by 12 on 10, 40 on 12, which works out to be 3.3 newtons. And welcome also to Chris, who just joined us. Good morning, and maybe you were watching the soccer or something. That got a bit late. Okay. Right, my name is Dr. Joseph Raja, by the way, so that you know who it is, and we've only just started. Right, okay, yes, I won't be telling you who won. Now, explain why the ball moves fastest at the bottom of the circle. When we are asked for these explanations, we have to show clearly in how we express the answer, our reasoning process in coming to that conclusion. Now, explain why the ball moves fastest at the bottom of the circle. Now, this is clearly an application of the energy conservation principle. Would somebody like to recite the answer they think to this? I can give you the microphone and you can speak it out and we can analyze it, or you can type it, but that might be a bit of typing. Anybody, yes, would like to explain it? Rosie didn't know. Explain why the ball moves fastest at the bottom of the circle. Of course, you have no doubt that it does, right? Because this is a common situation whenever everyday life, when you feel a bit bored, you might take a keychain or something that's connected to a chain, a bunch of keys or anything like that, and just whirl it around in a vertical plane. And of course, you know, it travels fastest down the bottom and slowest when at the top. Somebody else is typing, centripetal force doesn't oppose gravity at the bottom of the circle. No, there wouldn't be any marks for that. It's actually very straightforward. Right, let me take you through this. At the top and the bottom, what happens? It's got more gravitational potential energy at the top, and it has less gravitational potential energy at the bottom. So what happens to that gravitational potential energy when it's coming down? It's going to get converted into an increase in its kinetic energy, and therefore it'll be traveling fastest at the bottom, and then when it begins to climb back up again, what's happening? Kinetic energy gets converted into gravitational potential energy. So when gravitational potential energy is a maximum at the top, that's when kinetic energy is a minimum because of energy conservation. So it will be traveling slowest at the top, and when it comes down the other way, gravitational potential energy decreases as it gets converted to a gain in kinetic energy, and therefore the speed of the object will be greatest at the bottom. So I would simply explain it like this. Very straightforward explanation. Gravitational potential energy is greatest when at the top of the circle. When traveling to the bottom of the circle, some of its gravitational potential energy, I don't say all its gravitational potential energy because even here it's above the ground. I would say some of its gravitational potential energy gets converted into an increase in kinetic energy when at the bottom of the circle. Okay, and then say because kinetic energy is equal to a half mv squared. So you're showing very clearly the logical reasoning step by step. Because kinetic energy is equal to half mv squared, more kinetic energy at the bottom of the circle, more kinetic energy at the bottom of the circle also corresponds to a faster speed, put within brackets v. That's the speed. Any question about that explanation? Anything further you wanted to ask? Do you follow that, both of you in particular, that attempted to answer that? Rose and Rosie, both, it wasn't a satisfactory reasoning or logic. You follow that? Okay. It's actually very easy, isn't it, when you look at it in terms of energy conservation? Because as it's traveling upwards, it's in the vertical plane. That's the big difference here compared to motion in horizontal plane. This is in the vertical, swung in a vertical circle. There we are. And that means, of course, that when it's going to come down the circle on this side, some of the gravitational potential energy gets converted to an increase in kinetic energy. And when it times back up the other way, that gain in kinetic energy gets converted back into a gain in gravitational potential energy. Then there was a question, but you can't say that all of the gravitational potential energy is converted to kinetic energy at the bottom. Better not to say that. I'll tell you why. If you take the zero of gravitational potential energy at the bottom of the circle, our gravitational potential energy is always assigned with respect to a 0 point. Normally we take the 0 point as the ground. So if you didn't specifically say otherwise, we are measuring potential energy in relation to how high it is above the ground. So the height above ground here at the bottom of the circle is not 0, otherwise it would have hit the ground and stopped going around in a circle. So in the common context of things, it wouldn't be good to say that it's 0 at the bottom. On the other hand, if you said with respect to the 0 of gravitational potential energy being the bottom of the circle, if you had specifically said with respect to the 0 of gravitational potential energy being the bottom of the circle, then you can say gravitational potential energy at the bottom of the circle is 0. And it has a non-zero value at the top. Okay, Rose, is that making sense, the distinction I'm making? Momentum isn't a clear-cut, easy way to answer that. I'll tell you why. Momentum is conserved whenever there is no net external force acting on something. In this situation, there is a net external force acting on the object. That is why the momentum of the object is actually increasing as it comes downwards, because the force of gravity that's acting on it and the tension force. So there are two separate forces. The result of that is that the momentum increases as it comes down to the bottom, and the momentum similarly decreases as it goes up to the top. But you then need to draw vector diagrams, and it will be a much more complex explanation. If you look at your physics exam paper questions, there's generally a very straightforward, easy way to answer it if you nail the most direct principle to apply to the situation. And that was the energy conservation principle here. Okay? Rosie, is that making sense? Okay. You understand? If you talk about momentum, then we've got to explain why the momentum is going to increase. We can't just say it increases. Why? And why does it decrease? Then we have to bring into effect the two forces. And that all becomes kind of a bit messy. This thing with the energy conservation principle was much easier. We'll look at the continuation of this question now. Here we are. Diagram 1 shows the top of the swing. Gravitational force is acting downwards. At the bottom of the swing, gravitational force acts downwards. That's logical towards the center of the earth. And then they've drawn a diagram 2, and that's probably where we are meant to draw certain things. Part 3 says, diagram 1 shows the gravitational force acting on the ball at the top and bottom of the swing. Right. And always look questioningly at diagrams. I immediately see that they've drawn these two vectors for gravitational force the same in length at the top and the bottom. Logically, that is how it should be, because the gravitational force mg is the same whether it's at the top of the circle or at the bottom of the circle due to the uniform gravitational field at the surface of the earth, because this is not a height that is comparable to the radius of the earth. Okay? Excuse me. It might be a meter or two at most, and across that distance the gravitational field strength due to the earth doesn't change. So therefore the weight force, the gravitational force on it, which is the weight, is the same whether it's at the top of the circle or at the bottom. That's why we have drawn those two weight force vectors. That's what the gravitational force is, the weight of the object drawn to the same length, acting on the ball at the top and bottom of the swing. Assuming the tension force is non-zero at all points, draw vectors to show the relative sizes of tension forces at the top and at the bottom. Okay. Using the same scale, I'm reading the rest as well. Draw the centripetal force on diagram 2 at these two positions. Okay. Now, we saw that our centripetal force equation was what? mv squared on r. Now, based on that, can you tell me whether the centripetal force will be the same at the top and the bottom, or will it be greater at the top, or will it be greater at the bottom? So, same, top, bottom, I want to know where it's greater. Just type it in what you think, each of you. Where is it greater, or is it the same? So, it's type same, or type top, or type bottom. Right, which one? Christine, okay, everybody thinks at the bottom. Good, so that means everybody had it correct logically. Where was it traveling the fastest? At the bottom, and therefore that needs the biggest centripetal force, mv squared on r, right? Clearly, centripetal force is the force that points, the resultant force that points to the center to enable a uniform circular motion. And the bigger the speed, the bigger the centripetal force that's needed, mv squared on r. So, at the bottom is where the speed is greatest, and the mass is the same, the object's mass doesn't change. Look at the things in this equation. Mass is the same, distance from the center is the same, right? Distance from the center is the same at any point on the circle. So, where the speed is biggest is where the centripetal force will be biggest. So, clearly we need to draw the centripetal force on diagram 2 at these two positions. The centripetal force, I'll come back to part C in a moment. I'll just draw this other one. And where's the straight line color? Okay. I'll draw it in this sort of purple color. The centripetal force will be the biggest at the bottom. So I'll draw it like that. It must point to the center of the circular part. And it'll be smaller at the top. Okay, there we are. That's what the centripetal force is going to look like. Fc. Smaller at the top and bigger at the bottom. and make it quite clear in the comparative sizes you use for the arrows so that it makes sense. Why is that? Very simple, because the speed is greater at the bottom of the circle. Now, coming to part C, diagram 1 shows the gravitational force acting on the ball at the top and at the bottom of the swing. Assuming the tension force is non-zero at all points, draw vectors to show the relative sizes of the tension force at the bottom and at the top. Now, this again, if you think of an everyday situation or when you've done this sort of thing, when can you feel the object pulling the most on your hand? Not when it's at the top, when it's at the bottom of the circle. It pulls the most on your hand when it's at the bottom of the circle. So, the tension force, draw vectors to show the relative sizes of tension forces at the top and at the bottom. So, the tension force will be greatest at the bottom. I'm going to draw it in an exaggerated sort of way. So, I'll draw it up here. That's the tension force at the bottom. And there's a smaller tension force at the top. Tension at the top and tension at the bottom. T at the top is smaller, clearly is T at the bottom. And that's consistent with our everyday experience. And let me explain further why this is. Okay. Now, our gravitational force is always acting downwards. The centripetal force here has to point to the center of the circular path. At the top, your gravitational force is pointing to the center of the circle, and don't forget the center of our circle is over here. The center of our circle is at the center. Okay, there. I think of it as being exactly at the center. I might not have drawn it very clearly at the center, but you can see that the gravitational force is helping to provide the centripetal force that points to the center. At the bottom, excuse me, your gravitational force is downwards, your tension force is up. And furthermore, the centripetal force we need to point to the center is also bigger at the bottom. So what happens? Our tension force at the bottom has got to be obviously larger than the top. Why? Because at the top, the gravitational force helps it to provide helps the tension to provide the necessary centripetal force. So the tension doesn't have to be as much. Down at the bottom, there are two reasons why the tension is going to be bigger. First of all, you need to have a bigger centripetal force because it's traveling faster. The centripetal force needed at the bottom is bigger because it's traveling faster. Next, the tension force has to fight the weight force because the tension force is upwards, that's in the direction of the centripetal force, but it has to overcome the downward gravitational force. So because of both those reasons is why the tension at the bottom is a lot more than the tension at the top. Now, any question, anybody, please ask me and I'm happy to go through that or explain any aspect of that. Either C or D. I think D was easier to see simply by mv squared on r. Wherever the speed is bigger, the centripetal force required is going to be bigger. And that was clearly at the bottom of the circle. So that's why we drew it like that. The next thing, down the bottom, the centripetal force needed is going to be bigger and the gravitational force is acting against the tension. So to provide that bigger centripetal force, the tension has to be bigger compared to at the top when the centripetal force needed is not as much and the gravitational force is helping to provide it. Okay, just type through and let me know, did you understand that totally clearly? Just so it gives me an idea if people can understand that type of reasoning. Okay, Rose is okay with that. Chris, Rosie, so you can't say the tension is zero at the top? No. And look at this in the question as well that pointed this out. It said here, diagram 1 shows the gravitational force acting on the ball at the top and the bottom of the swing. Assuming the tension force is non-zero at all points. So it is very clearly there, Rosie, in the question where it said assuming the tension force is non-zero at all points. So therefore, the tension force is not zero at the top. Okay? Right. Now, but interesting situation that I would have spoken about nevertheless. What happens, and think again of an everyday situation when you're actually doing this, whirling an object attached to a string in the vertical plane. As you slow it down, what's going to happen? It's something different is not going to happen down the bottom of the swing, but as you keep slowing it down, what happens? There will come a point when it won't go along that circular path anymore. It will collapse downwards. Right. Why is that? Because if the tension force drops down to zero, what happens? The gravitational force on it will cause it to do what? Just to accelerate vertically downwards. Right? If the tension force at the top, remember the tension force at the top is smaller than the tension at the bottom. And of course, how small that is depends on the speed, because that determines how much of centripetal force is needed. Now, if you made the speed go down and down and down enough to make the centripetal force needed become zero, then what happens? We don't need any tension force. The gravitational force will actually make it just fall down due to gravity. Rosie, does that make sense? And of course here, it said it was non-zero at all points. Okay. Then, now we'll get to part E, which is a simple calculation, I think. Show that minimum speed the ball must have when at the top is 3.43 meters per second. Explain your answer. At the minimum speed, now let's say centripetal force is going to be the force towards the center. The tension plus mg must be equal to mv squared on r. Now, the centripetal force needed T plus W, the tension plus W, right, which is mg of course, provides the centripetal force. So that's going to be equal to mv squared on r. I can do it like this, otherwise I could have done it by writing down an inequality. But if I write it with an equation, mv squared on r is equal to T plus W at the top over here. Right? Now what happens? If the tension force becomes zero, it will fall if T becomes zero. So if the tension force becomes small enough that it becomes zero, it will fall vertically downwards. It won't keep moving in a circular path. So show that the minimum speed the ball must have when at the top is that. That would be for it to keep moving in a circular path. So therefore, we don't want T to be zero. So our mv squared on r, write it here, mv squared on r for T to not be zero, it must be smaller than, to not be zero, that it must be greater than W. Because if T is zero, it will be equal to W. But can T be zero? No. So For it not to be 0, it must be more than W, so that there is some tension, T. So that's why I'm saying that mv squared on R should be greater than W. So I can then write down saying, from here, we get to this, mv squared on R must be greater than W is mg. So what happens? The mass cancels out on the two sides. B must be greater than the square root of g times R. If you take the g and the R and put that in there and get the square root, let's see what we get. We know that I think we gave the numbers on the previous page. G, of course, they said to use 9.81 and the radius was 1.2. 9.81 and 1.2. Okay, so if I use 9.81 and 1.2, B must be greater than the square root of GR. That means it needs to be greater than the square root of 9.81, 1.2. So B needs to be greater than the square root of 11.76. And when you get the square root of that, let's see what we get. It needs to be greater than the square root of that, which is 3.4 meters per second. So the question here said, I'll come back to the board if you want to write it down. Here 3.43, which is what you get if you put that to three significant figures. Indeed, that's correct, 3.43 at the top. So the minimum speed is when that is equal to, so that's the limiting case, that next decimal place we include it is. So therefore minimum speed is the equal to speed. That's when it will just begin to fall down. We can say minimum speed will be 3.43 meters per second. Any question, anybody, with that? No? All's good there? Okay, good. The ball drops to its minimum speed of 3.43 meters per second at the top of the circle. Okay, that's up there. This is a good part of this question. I like this. Using conservation of energy, and they even helped you by telling you what to do, show that the angle at which the tangential speed of the ball is 4 meters per second up there. This happens where it's at 4 meters per second is when theta is 34.9 degrees. Right. Conservation of energy they said as well. And we also used conservation of energy earlier on in the question. Now, if you draw, let me draw a line here. And I'll use, okay, whatever color it comes in. Right. So we'll draw a horizontal line. Just okay, that looks horizontal enough to me. Right. Look at that horizontal level there. Now, at the top here of this circle, they told me the speed was 3.43 meters per second. So I can just put a sort of a blob at that point. There. 3.43 meters per second. Naturally, why is this speed higher? Because at the red spot point at the top of the circle, it's got a maximum gravitational potential energy and minimum kinetic energy. So at this point, it has a little bit less gravitational potential energy and therefore a bit more kinetic energy. And that is why the speed at this point here, when it's not at the top, is a higher speed of 4 meters per second as opposed to 3.43 at the top. Okay, there. Now, you can calculate this height based on the difference in kinetic energy. I can calculate the difference in kinetic energy. We can put it as delta KE will be half mv squared, meaning at 4.00 v squared, minus the smaller kinetic energy at the top of the circle, 3.43 squared. There. That's what the difference in kinetic energy is going to be. How did I get that? That's really just substituting into a like half m v2 squared minus half m v1 squared. And then of course that's meant to be squared. And then I can simply take half m outside the brackets and put v2 squared, which is like the 4 squared, minus v1 squared, which is like the 3.43 squared. Okay, so that's how this came about. And if I calculate the potential energy difference, delta PE will be equal to mgh. The difference in gravitational potential energy is mgh. So, energy conservation is mgh, where h is the height difference. H is obviously this height difference between these two positions, the vertical height difference that I am pointing to now. That difference in height there is h. Mgh is going to be half mv squared, or half m times this 4 squared minus, we erase some of this here, so there's a bit more room. 4 squared minus 3.43 squared. And then the m's cancel out on the two sides, and we can calculate h as being 16. 3.43 came about from finding the square root of something else. That was 11.6. Change sign plus 16. Just doing the arithmetic here only on the calculator. Nothing complicated. Excuse me, sorry, I've got a bit of a bad throat. So we divide it by 2. And then you divide by 9.81, which is what they told you to take G as. And that gives us 0.2158, and we can get the final answer correct then if we don't reduce significant figures too much. 0.2159 in fact. Meters. That's this height difference here. I'll just draw it like that. That height difference there. So, now if you look at this triangle, somebody asked me a question. Let me see what the question was. Should there be a minus between the 4 squared and 3.43 squared? Yes, there is a minus. This one here. See, that one there? That's the minus there. Right, that was there. Maybe it didn't appear properly. Is that making sense, Rose? Because I've got 4 squared minus 3.43 squared. Okay, right. It's not that you thought, why is there a minus? You thought there wasn't a minus, but there is a minus. Okay. So, mgh is half m v at 4 squared minus v of 3.43 squared. That's the difference in kinetic energy, is the difference in potential energies. So I've got that height. Now, of course, I can calculate what this side of this triangle is going to be. I'll just put that in a different color so you can see that here differently. I'm going to get this distance D. Right? Or I'll call it, let's call it D. That height D is going to be what? 1.20 meters minus this 0.2159. And that gives us what? When we do this subtraction here, that gives that distance there as being 0.984. 0.984 meters. Okay. Once you've got that, then it's not a problem to calculate this angle theta, because that's going to be what? We can get the cos of that angle, adjacent on hypotenuse. Cos theta is d on 1.20. So I can say here, cos theta is the adjacent side d divided by the hypotenuse length, which is 1.20. So what does that mean then? 0.984 divided by 1.20. Let's begin by wrote a long letter. I meant to write a C and wrote an S. Cos theta will be 0.984 divided by 1.2. And that's 0.8201. Let's begin by the cooking right here when you get our final answer. Cos inverse of 0.8201 let's begin by for the angle theta. So I hope it's on degree mode. Yes, I think it is. And where are we? There's the cos on this. Okay, here we go. Cos inverse. Yes, sure. Inverse equals. Let's begin by 34.9. Yes, indeed, that's correct. 34.9 degrees. Excuse me. Okay, any question, anybody? Now, this would have been a nice question if we were doing this over a series of days, so I could have given this as a homework question, because I know it was a bit of arithmetic there. Right? Ask me now if there's anything that's not completely clear with that solution. Chris is typing something. And somebody else is as well. Here, what do we have? Let's begin by the height. How did you get the height? Okay. I'll wait for any other questions quickly. Type them through so I can cover anything else that you need to get. Chris, are you asking me how did I get this h here? Just type yes or no if that's the height h. Is that what you're referring to? How did you get the height? Are you asking me how did I get that h? Or did you mean this d? Okay, this h. Now, understand the logic of this. That was at the very beginning of doing this part of the question. Because, and remember they gave you a hint as well, by using a conservation of energy. So what happens? The difference in this height, mgh, that vertical height difference, is the potential energy, mgh. That equals the difference in kinetic energy. That's going to be half m v squared here minus half m v squared at the top. Half m times 4 squared, when the kinetic, that's the kinetic energy here, minus half m times 3.43 squared, which is the kinetic energy at the top. So by getting the difference in kinetic energies there and equating it to mgh, where h is the vertical height difference. That's what I've done here. Look at what I'm pointing to right now. mgh, where h is the vertical height difference, mgh, is a half m times v2 squared minus v1 squared. v2 is the 4 meter per second, v1 is the 3.43. Right? Half m, v2 squared minus v1 squared. Chris, is that making complete sense? Please let me know so I've understood if that's what you are asking. Right? Okay, you got it. And then of course, once I got the height difference h, we get this side of this triangle by subtracting that h from the radius, which is 1.2 meters. See, I got that side d of the triangle. Look at this, the side d of the triangle here. Here's our triangle. I'm getting this side d of the triangle by subtracting the h from the total radius, which was 1.2 meters. That's why I wrote them in the two different colors as well. And that's 0.984 meters. And when I've got that, I can simply use the cosine trigonometric ratio to calculate the angle theta. Okay. Nothing further, anybody then? We can move on to the next question. Okay. There's somebody typing something. Let me see what that was. Right. Okay. Chris was all okay. Who was typing just a moment ago? Is this merit or excellence? This was a question that there were different parts of it, right, all the way through to F. So clearly, if you answer it in any of them, you would get marks that would count. But this part of it came to the excellence part, obviously. Right. But was that very difficult? Because it is logical, since they kind of guided you through the solution as well. You have the height difference here, which is obtained by the difference in gravitational potential energy and equating it to the difference in kinetic energy. And there was the hint as well to get you thinking the right way.